Thank you very much, Ben, for the introduction and for the invitation. So this talk is a bit of a review talk in some way. There's been many results over the past, let's say, 10 years, and also a lot of results over the past 5 years on delocalization of eigenvectors. And this idea, I'll present some of my results, of course, but some others too. So there's several works with different people. So Nishia Chen was a student at UChicago. Gelo Cipolloni is a postdoc at Princeton, Patrick Lopato at Brown, and Daryl Shea is a student at Brown too. So the first start would be to start to define these words. Okay, so in particular, delocalization. The model I'm considering random matrices, and actually I think I even define eigenvectors, so you'll be fine. So what I like to think of when I think of delocalization is about the study of what's called disordered quantum systems, especially because the word makes more sense to me for delocalization. So what is a quantum system? I'm going very fast because I'm not a quantum mechanics guy, but you take a configuration space sigma. So for instance, R3 can be an electron moving into gas, Z3 on a metal, maybe of a lattice. But actually what we want to consider is kind of the easiest case of a one-dimensional for 1 to n. Okay, then we're going to have a matrix instead of an operator, but things makes it easier. Then you have a state space, which is just here Rn, which is R2 of sigma. And a wave function, so a particle will be described by, well, something which is normalized to 1, so it's just a vector on the sphere. Okay, that's kind of the idea. And what we call the Born rule a bit is just that if you take the entries of this vector squared, you have a probability since sum to 1, and you can understand this as a probability of finding this particle at a configuration X. And so this can help understanding words like localization, delocalization, because you can localize a particle into a certain number of sites with this probability. Okay. So then the dynamics are often described by the self-adjoint linear operator, which in this case is just an n by n random Hermitian matrix. Okay, so that's why just a matrix, and then we can make it random if we consider disordered quantum systems, and we consider an n by n random matrix, and I'll kind of describe the whole dynamic. So the entries of the matrix, we can consider them transition rates from a configuration to another, and then I'm putting here notation more so than definitions. So λ1, λn will be the eigenvalues, okay, and they'll be ordered in this way. I don't think it matters too much in the talk, but I'll still order them that way. And U will be the eigenbasis, and U1, UN the eigenvectors. Okay, and something which is very important, actually, I'm going to recall in a few slides, is that they are normalized. Okay, they sum to 1. To understand scalings and things like this, it can be very important. And I did promise I would define eigenvectors. We have SUK equal lambda k. Okay, so there is a somewhat of a belief or conjecture. Okay, and as any grand universality conjecture, it is wrong. Okay, in some way, but there is a belief that there is kind of two main behavior for all these operators and all the disordered quantum system, if you have enough disorder, is that the system can be either in what's called the insulating phase or localized phase. So what does that mean? It means that the eigenvectors are localized, and here I put the definition. You have a subset of entries, okay, which is very small, where most of the probability mass is. Okay, so if you look at the particle, the probability of finding a particle is very high into few indices, okay, few states. And if you look at eigenvalues, well, it's basically Poisson local statistics. They're basically independent of each other. Okay, so if you want a very easy example of such a system, Hamiltonian of a system, well, you just take a diagonal matrix with IID random variable. Okay, then of course the eigenvalues are independent; they're IID, and the eigenvector, well, they're only localized onto one entry. Okay, because it's a diagonal matrix. So the let's say particle with probability 1 will be only on one configuration. Okay. So the other phase is called the conducting phase. So here eigenvectors will be delocalized, and for now I will define delocalized by being not localized, if you want. And interestingly, nearby eigenvalues will be strongly dependent, and more than that, there's a specific dependent structure, which I will not define too much in this talk since I will focus on eigenvalues. But what's called the Wigner-Dyson meta-local statistics, if you know the sine kernel, Airy kernel, this type of Percy kernels, they kind of behave in this way. So the typical example, which is less trivial than this diagonal matrix, is what's called the Gaussian orthogonal or unitary ensemble. So here I put an example of what a delocalized eigenvector would look like. So what is this Gaussian ensemble? So I'm going to present here the Gaussian orthogonal ensemble. And actually, all this talk, I'm going to talk about real symmetric matrices, but all the results convert to Hermitian matrix up to changing constants, but there will no trouble for this talk. So the Gaussian orthogonal ensemble, so it's not an orthogonal matrix, okay? It's a matrix which is symmetric and full of Gaussian, okay? And my scaling will be, oh, sorry. My scaling will be that, okay. Okay.
Yeah, control L, try control L.
Perfect. Okay. Okay. So the all Gaussian, and I put the variance 1 over n. Okay. This will help basically the norm to be of order 1, and so you have eigenvalues that are of order 1. Okay, between -2 and 2 actually. And so why it's called Gaussian orthogonal ensemble is because it is invariant to orthogonal conjugation. So if you take your matrix H and you conjugate by a deterministic orthogonal or independent orthogonal, then you have the same distribution as the Gaussian. Okay. So what does that mean for eigenvectors? It means that if you could take an eigenvector, well, you can rotate it as much as you want, and you have the same distribution as before. So you don't have much choices. You have to be uniform distributed on the sphere, right? It's kind of the only possibility. And actually, that's true. And even if you take the whole eigenbasis, it is basically what's called hard distributed or uniformly distributed on the orthogonal group. Okay. Also, an important fact for GOE, but interesting fact is that the eigenvectors are independent of the eigenvalue. Okay, you can look at them separately completely. But we'll see that when you look at models that are not orthogonal invariant, understanding eigenvalues are very important to understand eigenvectors. Okay. So I put this phrase, eigenvectors are really trivial for the GOE, right? There's nothing really interesting more than that. They're uniform on the sphere, so you can do.
What is that picture?
Yeah, this one is just on. Oh yeah, I was going to say if you want, it's true for even finite n. Okay, n equals 3. Okay, you can just plot anything. It's not a high dimensional thing. Like it's true for anything. So I just plotted a sample of the middle eigenvector of a GOE 3, and so you can see that it's uniform on the sphere. And actually, I didn't explain the top picture. If you want, here I have the indices from 1 to n. And if you look at this quantum system, right, it's basically a complete graph, right? You can go from any rate to anything because every entry is Gaussian. And not exactly the same, but in distribution the same. Okay, it's kind of the same transition rate. So even though they are trivial, what we can do is basically say, okay, we want to prove some universal property of eigenvectors of other models. But we're going to see models are not orthogonal invariant. So eigenvectors will not be uniform on the sphere. So I cannot prove this. This is wrong, right? But what I can do instead is say, okay, I can start from the GOE and see some quantitative estimates that can be deduced from the fact that they're uniform on the sphere, and try to prove these quantitative estimates, okay, which can say that they behave in some way similarly to this model. Okay, so it's a true reference for other delocalized systems. And actually, this Gaussian ensemble are even reference for many deterministic systems. If you heard the zeta function, some quantum chaos theory stadiums and things like this, you can believe that this is a true reference system for many of those. Okay. Okay. So I'm going to example of this quantitative estimate or thing we can prove. Okay. So the first one is what I'm going to call delocalization. Okay. So that's in the title of the talk. It is the following. So, okay, I wrote it in this way. So if you take an eigenvector entry, or basically the maximum is of order square root 2 log n over n. So here it's an upper bound, but I can tell you it's actually lower bounded also. So I remember you scaling that sum to 1. So let's think of this type of scaling. Well, the 1 over square root n, it means what? It means if your eigenvector will be deterministically kind of delocalized, since a sum to 1, right, then every entry would be just plus or minus 1 over square root n. Right? It would be exactly delocalized. Every entry would have exactly the same value. Okay. But here, it means that it doesn't go far from that, because the largest entry is 1 over square root n, but there's some fluctuation over the square root 2 log n. Okay, so it's not exactly deterministically distributed, but pretty close to it. Okay, and you can see an example here where I put the entry square of an eigenvector. And the square root 2 log n, why? Well, you have to compare an eigenvector to an IID Gaussian vector. Okay, the maximum of n IID Gaussian vector is square root 2 log n, and that's basically the same idea. Okay, so you have exactly that. Of course, they're not IID since it's sum to 1, but this is very weak correlation. It basically doesn't matter at this stage of bounds. Another property here, which basically states that this is correct, this kind of idea that eigenvectors are ID Gaussian, is that if you take, let's say here I put fixed number of eigenvectors and fixed number of entries, well, they jointly converge to IID Gaussian. Okay, we hear the dimension going to infinity. Okay. So these results are pretty old. Okay, I think it's that from Borel, okay, in the early 20th century. Then Levy, and then Diaconis and Friedman managed to put the I going to infinity also. You can try to take a large number of entries. If you don't take too large, it's still true. And Jung also generalizes to a large number of entries and large number of eigenvectors. As long as it's not too big, then you can still prove this result. Okay? So I have a convergence in distribution. So here it's a sample of one entry of an eigenvector. I put absolute value to avoid any problem with phases, since eigenvectors are not very well defined. Okay? There's plus or minus each time. So to avoid this problem, I just put absolute value. Okay, so that's two examples of one. I'm going to present a third one, which comes, at least the name, and comes from a different part of math, but it's also quantum unique ergodicity. So what is that? The idea is to say, okay, the previous bound said that the largest entry cannot be too large and cannot look like it's deterministically distributed. But here it's different. So okay, I take the probability of being on a certain number of indices, okay, which is this, the sum of UK square alpha squared. Okay, this is basically the probability of being on those indices. And I compare it to the uniform distribution, okay, which is just I over n. Okay, so how close to the uniform distribution this probability mass is on any set of indices. Okay? And you can get a bound with very high probability up to a certain error. Okay, if you look at the error, as long as I grows with infinity, this is a good error. Okay, if I is over the constant, is not very interesting, but it's still true. The second born here is basically to say how eigenvectors are orthogonal to each other. So the matrix is real symmetric. Eigenvectors are orthogonal to each other. But here, basically, it says that you project them onto a sub-indices, they still look orthogonal. Okay, it's not just some kind of structure in the eigenvectors that make them look orthogonal. They're like orthogonal everywhere. Okay, it's really that. Okay. And with a specific error, and this error is actually optimal. We're going to see it later. So, okay, quantum unique ergodicity, that's kind of fancy word. So this fancy word doesn't come from random matrix theory. They come from quantum chaos theory. It's a big conjecture by Rudnick and Sarnak. So okay, I'm not a quantum chaos theory specialist, but the idea is that if you take negatively curved compact Riemannian manifold and you look at the eigenfunction, the Laplacian on them, then as k goes to infinity, the probability mass of each eigenfunction as high energy goes to the volume measure. Okay, it's kind of the uniform distribution. To see it simply, I put here one example. So I think this sometimes is called the Barnett stadium. Okay, so it's like an angle. Here you have two circles. So it's true negative curvature. And you can look at the specular reflection on that and look at the Laplacian on that. And if you look at eigenfunction, well, at high energy, they're going to look more and more and more uniform. Okay. And what's important here is the unique. The unique means that it's along the whole sequence. It's not a subsequence, it's really true sequence. So it's supposed to be true here because you don't have any scarring, okay, of like potential reflection that would create a lot of mass. So this is a big conjecture, which is, to my knowledge, very far from being proved in generality. It's been proved on very specific surfaces by very strong people, or for subsequences. Okay, so for subsequence or an averaging over k, this is true for many types of surfaces. Okay. So now I give you three properties of eigenvectors of the GOE. Okay? And I didn't give you any proof, but you can prove all of that by just using the fact that you're uniform on the sphere, okay, or hard distributed on the orthogonal group. Okay, you have exact distribution, so you can do computations. So now the question is, does it hold for more than Gaussian? Okay, that's a universality problem. So I'm not going to do for any disordered quantum system, okay, because I'm very far from that. But what we can try to do is do for more random matrices. Okay? So the idea is, instead of taking Gaussian random matrices, we can take more or less any nice enough distribution. Okay? So what I'm going to do is called the generalized linear matrix. So it's self-adjoint matrix. The entries will still be independent. Okay, that's important. They'll be centered, and the variance instead of being 1 over n, basically it's of order 1 over n, and they don't have to be IID. Okay, you can take different variances as long as they sum to 1. Okay, so normalization will be important, more technically than philosophically, but quite important. And then a moment condition on any moment. Okay, the moment exists basically. Okay. So maybe I'll just explain quickly, and it'll be important for the rest why I use this normalization. So there's a very famous theorem is that if you use this theorem and you look at the eigenvalues, well, the eigenvalues will converge to the semicircle law, okay, which is like this. Okay, so you take the empirical spectral distribution of eigenvalues, it will converge to a semicircle. And this helps a lot in many technicalities. Okay, I will leave this picture here because I might use it later. So, of course, this is a complicated model if you don't know any random matrices. The idea to do is you use in your head this example. You take a matrix n by n plus or minus 1 over square root n everywhere with probability 1/2. Okay, so you launch a coin at every entry, and heads you put 1 over square root n, tails you put minus 1 over square root n, and now you have an example. Okay. In particular, this example is quite important because it's kind of singular in the random matrix case for several reasons. Well, one special reason, but that's the idea. Okay. And of course, if you have IID Bernoulli matrix and you rotate it, it won't be a plus or minus 1 anymore. Right? So there's no rotational invariance, no orthogonal invariance for this model. So you cannot use what we did before. But if you look at two eigenvectors, well, they look very similar. Okay. Of course, that's just my eye, but they do seem to look similar.
Why did this should they go up to 2 right?
So it's okay. It's a finite n issue. There's a log n and there's a log n after.
Very unconvincing.
That's true. That's true. I'm wondering if no, I don't think I took Hermitian, but I think the problem is the finite n on the log, and then there's a log n term before being a distribution, and I think this kind of creates problem. But that's true. It's not impossible to project on the sum of the indices. I didn't take the whole thing, but I don't think so. But okay. Okay, so now I'm going to give some results that me or other people did about these results, these previous quantities we want to prove. So in the first one on eigenvector delocalization, I put the GOE that we had a few slides ago, and this is a result I did a couple of years ago with Patrick Lepato. So the first one, the first inequality here is basically to say that the square root log n is correct. Okay, if you look at actually the largest entry of the whole eigenbasis, it is of order square root c log n over n. Okay, the constant here, however, is not optimal in this setting. Now, the second one is a bit. I didn't give it for the GOE, but it would be true. Is that you can look at an eigenvector at every eigenvector on any direction. Okay, you can fix a direction and look at this eigenvector, where the largest entry will also be of order square root c log n over n. Of course, you cannot put this supremum inside the probability, because if you take q equal uk, then you have one. You have to fix the direction before. And finally, we were able to actually reach the optimal constant at the price of losing some probability bound. Okay? But for one eigenvector entry, the largest is bounded by square root 2 log n over n. Okay, we managed to prove this result for all generalized linear matrices. Okay.
Probability should be much quicker.
Oh, much quicker than this, probably, yes. Then, as quick as GOE, probably might depend on the tail of the moment or anything. It's not completely clear how much it should decay. But yeah. We'll see, hopefully, at the end, why this n minus c comes.
With the Gaussian case, like the way you've written it says for all d, there it's k, like k, there exists kappa. Kappa is large here. First estimate. Like there's no control on kappa.
There is a control. I just didn't put the actual full bound. Basically, this n minus d. Okay, what I mean is like this is n minus 1 minus kappa squared or something like. So you can choose a kappa to have the d you want, basically. If you want n minus 4, you can find a kappa, which would be correct.
But it's like it's very large. Like for the last estimate, it's not going to be like sub-exponential on the right-hand side.
This one?
Yeah.
Well, this one is very bad. Like this one, if you want,
But the truth
Can you go the other way? So every kappa there is a T. So maybe that's
okay, for this one or for this one? Sorry. For this one, I wrote it this way, but there's an explicit value here, depending on kappa, which is correct.
Oh, so it's the other way. For every kappa there is a T. Not for every T there is a kappa.
That's both. It's both, right? It depends. Let's say you want n minus 50 bound, you can choose kappa so that you have n minus 50, and you know exactly which one you need to pick. I guess that's why I wrote it down.
Yeah.
Here, for every kappa, there is a C, but the C is lower bounded, or you cannot take C, upper bounded. You cannot see as high as you want here. That's a problem.
I mean, you know that.
Well, no, we managed to prove that, but it should not maybe not be upper bounded. Our result is weaker than what
do
we
you have a lower one on the probability?
No, it's very unexplicit. Okay. Yeah, we're going to see at the end, hopefully, why. It's come from level repression estimates and things like this on eigenvalues. So it's very different. Okay. So yeah, maybe it's a bit of history on these delocalization bounds. So yeah, there's quite a literature on that. I put only a few for this type of model that we have and for this type of bound. So the first kind of breakthrough was for this square root n to get at the bottom here for the infinite norm by Ehrstein and Yao about 2008. I think they managed to get it. And then it was improved by Tao and Wu and also the Shironian later to get better and better bounds for different models, et cetera, et cetera. For the isotropic one, there was kind of the same team of people, Knowles and Yin, and after Bremen, Knowles, Yao and Yin, managed to prove this. The square root log n, so the optimal order at the log, was actually obtained for the infinite norm of an eigenvector by Wu and Wang in 2013, but there was some catch. So it was only for IID bounded random variable. Actually, it could be improved for sub-Gaussian by using the kind of Anson-Wright inequality by Rudelson and Vershinin, but only for eigenvectors in the bulk. So what do I mean by that is that, remember that I ordered the eigenvalues by lambda 1, lambda n will be here. And here I need to basically do a cutoff. I cut the edges. I only consider eigenvectors where the eigenvalues is in this semicircle. Okay. For reasons, sometimes the edge is easier, sometimes it's harder. In this case, it was harder. And you can only consider the bulk here. So that's what I mean by alpha n 1 minus alpha n. And the square root 2 to our knowledge was only known for GOE. Okay, so that's the first time I managed to prove a universal result up to a constant on delocalization. One note: if you take the G, if you take a complex Hermitian matrix, the 2 becomes a 1. Okay, this is just so you know. One result also that is not mine, but is very important here, is that indeed we have this sort of convergent distribution to IID Gaussian, okay, in the same way. So there's been quite a lot of different work to put in this, and actually it's still not known in full generality. So by Knowles and Yin, Tao and Wu managed to do it under a moment matching condition. Then there was a nice paper by Bourgade and Yao who managed to push this, but it was not for any indices like this. It was either you fix an eigenvector and you take different entries, or you fix an entry and you take different eigenvectors. So you couldn't take like any entries of any eigenvectors. And actually, I will explain why it's complicated later on. And Marcinek and Yao managed to push that and prove for any eigenvectors, any entries, but only in the bulk again. So it's still at the edge, a bit of a problem. So technically, the picture is not fully complete. Okay. If you take an eigenvector at the edge and an eigenvector at the bulk, we don't know that they are jointly Gaussian. Okay, the next result I wanted to tell you is about this QUE quantum univerisity result. So I didn't remind you the GOE case because it's exactly the same as above. Okay, so we managed to prove the same bound, okay, with the optimal error here. And actually, we can manage to prove it's optimal, this error. So here there is somewhat of a catch. So we can prove a CLT. Okay, so actually this probability mass converges to a Gaussian if you rescale it by this error, but only for a certain type of indices set. So they have to grow with n to the epsilon, which makes sense, the CLT, so you need some averaging, but not too much. Okay, in particular, we don't want to see the correlation of the eigenvector. So it makes sense that they should look like IID Gaussian because we don't see that they sum to 1 in some way. However, at the edges, so now if you look at eigenvectors only here and there, then things are easier for some reason. And we can prove that they converge to a Gaussian regardless of the size of the index. Okay, and the variance is a bit more complicated. But if you take I way smaller than n, this just becomes that. Similar. So at the edge here, it's a bit easier. In particular, the first bound, the quantum univerisity bound, uses a previous result by Bourgade and Yao, and Bourgade, Yao, and Yin, especially in 2018. Okay. So now I'm going to tell you about a kind of third or fourth way we can.
What was your assumption about the matrices?
So they were just finite moments.
Some number of moments.
All moments.
All moments.
So the notion of quantum univericity, we can kind of generalize it by what's called this eigenstate thermalization hypothesis. So what do I mean by that is instead of looking at the probability over a set of indices, you can look at the deterministic matrix and look at this quadratic form in UKUL. Then this what's called ETH tells you that the eigenvector actually cannot diagonalize any matrix. It's kind of the idea. It's what thermalization is in this sense. They diagonalize up to an error, which depends on the Hilbertian norm of the traceless part of A. But this, I won't talk too much about this type of error. But it's a harder form because it's a direct generalization. Right? If you take A to be a diagonal matrix with 1 where you want the set of I, you recover exactly the QUE. Okay, so it's just a more generalized version. So this is introduced in the 90s by Deutsch and Srednicki. And it was proved for Wigner matrices by Cipolloni, Erdős, and Schroeder, and then Einheck in different papers, the edge, in the bulk, the optimal error or not, etc. There's different papers. And for generalized Wigner matrices, the model, which is not IID that I showed you, is also been proved this year.
Why do you expect? I don't understand what's happening. Sorry. Can you explain?
Okay, so basically you take a matrix A, a deterministic one, and you look at the quadratic form UKAUL. Okay.
You are your random vectors.
UK and UL are the random.
I guess an n by n matrix, like
yeah, deterministic matrix A of norm 1, of norm 1.
I see.
And the idea is that in the eigenbasis of the eigenvector, around the basis of the eigenvector of a Wigner matrix, it will look like a diagonal matrix because it looked like this delta KL 1 over n trace of A. Okay, so that's the eigenstate thermalization hypothesis. It's supposed to be true for many different systems, not just random matrix system. It's a physics paper here, but this can be proved in the context of random matrices. Okay, so it's like any matrix.
A delta A, what does that thing mean? Brackets A delta KL.
Oh, sorry, yeah. So the brackets are 1 over n trace of A. That's a normalized trace. Okay. And this is just mean that if you take K and L different, it's supposed to be small, to be close to 0. If K is equal to L, this is supposed to be 1 over n trace of A.
So it sort of looks like even like a constant times an
yeah.
identity matrix.
So. Yeah. Exactly. Up to an error, which is that. And actually, the error being optimal can be proved. So in one of the photo paper by this team, they managed also to prove that if you look at indices in the bulk, so you remove the edges again, you look only in the middle, this converge to a Gaussian. Okay, so you have a central limit theorem with the optimal error here, which is the same as here. This condition looks complicated, but in a way, it just means that you need some averaging. Okay? You need some growing amount of entries that sum, okay? Because this is a central limit theorem. If you take only a finite amount, then there will be nothing happening. So you need kind of something growing, and you can quantify this by the Hilbert-Schmidt norm. So one thing important is that actually all these results, even the previous one, here it's only.
Can I just ask if the U's are just chosen to be uniform R measure, then that's what you get.
This would be true. I think this would be true for that. Yeah.
So, no, but I mean, without the n epsilon, you get 1 over root n times the Hilbert-Schmidt norm. Is that the?
Yeah, because
It's not obvious to me.
I don't have a good intuition of the error, to be honest.
The other thing I don't understand is, sorry, what controls the size of it?
The norm has to be here 1, smaller than 1.
Oh, there it is at this one.
Yeah.
I see, but then it can be too small.
Yeah.
So no, but this has to be some kind of. We're just trying to understand what this condition is. Does it mean that the eigenvalues kind of behave reasonably, for example?
Yeah, at least don't grow with n.
I see. So the Hilbert-Schmidt norm is big, you're saying.
Well, big, it's n-1 plus epsilon here, right? Still, it can be small. It's not too small, basically. Like if it's too small, basically there's no averaging happening. So there's no CLT, like there's nothing happening.
The Hilbert-Schmidt norm is greater than the actual operator norm. The operator norm can be smaller.
Is there a normalization by having your Hilbert-Schmidt form? Or the Hilbert-Schmidt?
A good question. I don't think so, but yeah.
I guess it's just because you subtract the.
Yeah, subtract the trace in the error. So I think there's no n.
I see. So you normalize by Hilbert-Schmidt form. So this is essentially an upper bound on the operator norm, or the ratio of the two.
Yeah, you mean this condition?
That the largest eigenvalue cannot be much bigger than the L2 max.
Yeah, but I mean, okay. One idea of me how I try to remember this thing, right, is that this condition basically is kind of similar to this condition here. Like, right, if you sum over I, you need I to grow with n. Otherwise, there's no averaging, and so this is not a CLT. Now, instead of looking at this kind of simplified way, if you look at the quadratic form with A, this translates to this condition. Like, you need to have enough terms in your sum, basically. This is if you expand this as a sum in some way, right? You need to have enough term big enough to have some averaging.
You can't take A to be the zero matrix.
Well, yeah, of course, right? That would be a problem, right? You would have a Gaussian.
Or you rank one matrix also.
Exactly, that would be a problem. So you need the rank to be big enough to have some averaging, basically. Okay. Yeah, but so one thing that in these papers and actually even previously, it's only the UK that we can do a CLT here, right? So it's only if you take K and L different, well, the CLT has not been proved. So we thought about this with the Giorgio Cipolloni, which was one for the previous team. And we managed to prove, basically, if you take any different matrices, different indices, if everything is in the bulk, then you have converged to a Gaussian. So you take different eigenvectors with the same value. So if K is equal to L, we know that this converges to a Gaussian by the previous slide. But now I'm telling you basically that if you take K and L, that can be anything, that can be different, and you can even take different matrices, then this converges to a Gaussian field, basically with a certain covariance. And the covariance is close to being IID. Okay, there's a lot of deltas. But of course, if the eigenvectors are kind of the same, then you have a covariance which depend on the inner product of A and B divided by the norm of A and B. Okay, so you can have a Gaussian field, which is anyway not too complicated, even though that looks complicated. But the idea is that if you have different eigenvectors, it will be 0. But if you have the same eigenvectors, then it depends on the matrices, and it depends only on these values, okay, which is kind of a traceless part of A and B. Okay. So this can give a deeper meaning, understanding of this eigenstate imagine hypothesis and this CLT. It's a normalized traceless. You remove the trace each time. Yeah. So it's trace is part of A and B. Of that. If you want an easy way, you can also suppose that trace of A and B are 0, and then you can remove the bubbles. Okay. Okay, so maybe I wanted to give a tiny bit of idea of proof of that. Okay, so the first thing I'm going to present is the kind of high-level idea of the proof, and then I will go deeper into every step. What are the problems that arise, or what is good, what is bad? Okay. So this method is based on a dynamical method, which was random matrices introduced kind of in a big way by Ederstein and Yao in 2008-9, and refined over the years. But the idea is the following. This big square is a space of generalizing the matrices. That's what it is. And W here is my matrix full of Bernoullis, plus or minus 1, let's say. Okay. And I want to prove result, everything I showed you for this matrix. So the first thing I can try to do is just do linear algebra and probability. I have a matrix, so I have something, some complex analysis, maybe with a resolvent or thing like this. And I can go pretty far. Okay, so that's what I mean by optimal control on mesoscopic scales. Okay, and I will show you exactly what you can prove, not too difficultly using that. Okay, so the first idea for delocalization by either Yin or the eigenstate termination hypothesis actually can be proved directly on the matrix using similar ideas. But sometimes you cannot, it's not enough. Okay, so the idea is to say, well, I'm going to perform an integrable dynamics. What I mean by integrable in the ways that I can do computation with them, let's say. But what's nice is that I'm going to introduce some Gaussianity. Oh, sorry. Okay, I did the same thing. I'm going to control L, right? I'm going to introduce some Gaussianity to kind of do computation. But what's nice is that these dynamics are going to do it for a long time. Okay, and I'll explain also what I mean by that. So the time can be way smaller than 1, okay, going to 0, but it has to be big enough so that I obtain enough Gaussianity to prove something. Of course, it's high level. I will explain more of that later. So now I can get my result for HT because I can do computation. But now you can tell me, okay, well, I wanted W. I didn't want HT. Right? The Bernoulli matrix doesn't have any Gaussianity in it. I cannot prove for it. The next idea is to say, well, I can choose an initial condition, which will depend on W and on T, so that basically I land close to W. I'm going to land close to W, close, close. But close means I can transfer estimate from HT to W. Okay, that's kind of the idea. So I can prove things for HT using the dynamics, and then I can come back to W in this blue disk, which is a very kind of okay, that's a high-level thing. If you think hard, it means that if you don't want to do dynamics, you can always do something, right? Because if you have the GOE, you know everything for the GOE. So everything in the blue disk, you already know. You can transfer estimate from the GOE to any matrix which is in this blue disk. Okay? And that's what Tao and Wu, for instance, did by the four-moment matching, the four-moment theorem. But unfortunately, a Bernoulli matrix is not in the blue disk. Okay? So we cannot prove things for a Bernoulli matrix directly only using the Gaussian. Okay? We need these dynamics to prove it. Okay. So first thing is how to obtain delocalization like this using only linear algebra or ideas like this. The idea is the following, okay? And it's actually very simple. It's just computing, well, it's not simple too. The idea is simple, and of course there's some work, but the thing is that, okay, I consider the resolvent, okay, which is this quantity, and I'd say, okay, I want to bound an eigenvector entry and do a trivial thing. Okay, I can write it like this. Okay, this is a trivial. But now they're positive entries, right? So I can sum all of them. This is smaller than the sum of all of them. But now, this, you can recognize it as the imaginary part of this. Okay. So actually, this is equal here to the eta imaginary part of the resolvent. So now I can directly, if I manage to bound this imaginary part of the resolvent, I bound the eigenvector entry. So in the bulk, you can take eta to be n-1 plus epsilon and prove that this is bounded. It's not easy to do, okay, but you can do it. At the edge, it's a bit different. Eta has a different scaling, and the resolvent vanishes with eta because the density here you see vanishes. Okay, so you can use the fact that you vanish, like a square root actually, to use the fact that you vanish here. But in any case, if you compare the two and these two, you obtain n-1 plus epsilon. Okay, and that's how you can get this proof. Okay, so basically proving delocalization at this level is just tends to bound in the imaginary part of the resolvent. Okay, if you're bounding correctly at the correct scales, you can just do it. Okay, so it's enough for that. However, if you want the optimal log n, it's not exactly enough. Okay, I put somewhat enough because this paper has similar ideas of this, not exactly the same, but similar ideas. But then you need to push very hard. You need to be optimal in your logs. Okay, and this is hard. You need very hard concentration inequalities. That's why they wanted IID bounded, and they pushed and pushed and pushed and managed to get the optimal, but only in the bulk. Okay, at the edge, it's too hard, and they managed to get log n instead of square root log n, which is already very good, but not optimal. However, for our result, we want the optimal constant, let's say. Then this is not enough. Okay, you cannot push this to the optimal constant everywhere, or maybe you can, but we don't know how to do it. To obtain here the exact bound. Okay, so here we need to do something else. For the eigenstate summation process, I will go quickly on that, and I won't go in detail. But the idea is similar. You can bound this term here, UK UL squared, by trace of imaginary part resolvent A, imaginary part resolvent A. Okay. So now instead of just the imaginary part resolvent, you need to bound this type of quantities, which is way harder to bound, but you can still do them. Okay, that's why Cipolloni, Erdős, and Schroeder did, and that's how they proved this result. Okay, so here it's more complicated quantity that you need to understand. In particular, it's enough for the ETH, but if you want the CLT, okay, converge to a Gaussian, then it's not enough. You need something more to understand the Gaussianity of it. You cannot just do it using just bounds. Okay, you need to prove a convergence in distribution. Okay. Okay, so that's kind of the first step where you can try to do linear algebra. So you see, you can still obtain some nice results. But if you want the deeper result, you need to go beyond that. So what you can do is using the Dasein-Bohan motion. Okay, so this is this integrable dynamics I told you about. So what is this dynamics? You take a big symmetric matrix full of independent Bohan motion up to the symmetry, of course. Okay, and you look at this dynamics. So here I put the Ornstein-Uhlenbeck version. Okay, with this minus HT/2. Okay, the reason why is because the GOE is truly invariant for this dynamics. Okay, just so you remember that the goal is a GOE. Right? Actually, I cheated a bit because I think the eigenvector is not really of this model, but it works. So you have a dynamics where the GOE is invariant. Okay, so you can hope that if you take time long enough, you look more and more like GOE, but hopefully you don't need time too big. But what's very nice for this dynamics is that you can compute directly the eigenvalue and the eigenvector dynamics. Okay? So what is the eigenvalue dynamics? Well, each eigenvalue is basically independent Bohan motion, but then you add some in the drift, some repulsion term. Okay, you see that this 1 over lambda k minus lambda L. So if eigenvalues goes way close to each other, but they tend to repulse each other. Okay, so they will never touch each other. Actually, we can prove for here beta equal 1 and 2, so it's good. Okay, they will not touch each other, but they can go very close still, but not touch. Okay. For the eigenvector, it's a lot more complicated. Okay, you see that every term depends on this lambda k minus lambda L. Okay, so even the martingale term depends on these gaps. Okay, so things are a lot more complicated. But there is one thing that's very important to see on these two equations, is that here the BKK and the BKL for L different than K are independent. Okay? The noise driving the eigenvalues is independent of the noise driving the eigenvectors. Okay? And this is a very important fact that we're going to see in the next slide. So how do we do this? I'm going to do a simple, I'm not going to do it, but I'm going to tell you a simple computation. Let's say you look at the variance of an eigenvector, but instead of taking just the expectation, you're going to take the conditional expectation with respect to the whole path of eigenvalues from 0 to 1. You say, okay, a condition on the eigenvalue path. Now it exists, it's there, it's deterministic. And I look at the expectation conditionally on that. But what's nice is that now all this term gets killed, because this is independent of the BKK. Okay? So I don't care about the martingale term anymore. And if I look at the equation, I just have a nice, well, nice-ish PDE. Okay, it's still quite complicated. But I have some kind of PDE which depend on this gap, lambda k minus lambda L squared. Okay? But it's somewhat parabolic. You can think of this as somewhat of a Laplacian. Okay? And you can try to prove a proof thing. And you can use actually a maximum principle, what you know about the resolvent, and everything to prove that this converges to 1. So this one way to prove the variance converges to 1 is just studying this equation here. And what's
I
nice?
think of this as, I mean, when I look at this, I always think of it as, you know, continuous time random walk.
Yeah, exactly. So it is.
The jump rates are
Yeah. That's exactly what it is. And actually, it generalized. Okay, so this is kind of 1 point random walk. Okay, you have one random walk that jump from side to side at the rates of this, and you can generalize it. So this looks very complicated, but what I mean here is that you can take any joint moment. Okay, you don't need to just the variance. You can take any joint moment, and this works. You have a multi-particle random walk in random environment. Depending on the eigenvalues, they all jump around. Okay? But you can still do it.
You have some. I know you have something where you can do this for different. Where it becomes kind of. Sorry, it's like a determinantal process or something, or something fermionic.
Yeah. Okay. Yeah. So okay, I don't go in this talk. I don't go in this talk about it, but yeah, we can talk about it after if you want. But yeah. Okay. Maybe I'll talk about it.
Sorry.
No, it's okay. Actually, here that's maybe related to what you're saying. This follows also a nice equation. If you take k and k the same, that's why the central limit theorem was easier for k and k the same, is because this follows a nice equation like this, and it's related to the determinant thing you were saying. However, if you take k and l different, then it's not nice anymore. And I'm going to explain to you why in the next slide, but doing the simplest computation one can do. So now instead of taking the variance, I'm going to take this joint moment. So I take 2 eigenvectors and 2 entries. Okay. I can use Ito's lemma on the process. I'm going to get these 2 things, which are the same thing as last slide, the nice part. Okay, parabolic, 2 parts. So this is nice. This is not a problem. However, there's going to be a last term that's going to add. Okay, and you see here it's like a 4 moment still, but now it's k alpha, k beta, l alpha, l beta. It's going to mix the 2 moments together to create a new 4 moment. And this is not parabolic anymore. This is not closed formula. I don't know what to do. Okay, actually, I've tried in my PhD quite a lot, things to do about it. That's how I find this determinant in this thing. But this is quite difficult. You cannot do a maximum principle. But what Marcinek and Yao found is that you can still use some energy methods. Okay? The idea is that even though it's not, if you want positive or negative, depending on how you define it, in infinity norm, you can look at the L2 norm, okay, over all configuration. I'm not going too deep into that, but you can use a different norm, and you can use a one-wall type inequality of that. And you can prove that the L2 is what you want. And then you have to transfer the L2 bound to the infinity bound using energy method. It's not easy, because this is quite difficult. Okay? But they can manage to do it using more PDE method, basically. And you can prove that this converges to 1 also, which is what you want. Okay. So this is now possible, but this is quite hard. Not easy analysis. But the analysis is only done in the bulk, so at the edge is still open.
What are many models?
Well, the paper is basically the design-able motion, only the dynamics part, and they can apply it to Levy, deform, Wigner, Jonas Wigner, Wigner time. Like they prove for any initial condition this works, and as long as initial condition. And that's what we did, for instance, in a paper with Giorgio, by generalizing this to any AI, any eigenvector, etc. You can generalize. Okay. Yeah. So maybe in the in the last few slides, I just wanted to tell you about this blue disk. Okay, how do you transfer estimates, right? So,
sorry, what?
I remember in the box there was a way to transfer estimate from HT back to W. Okay, in this, sorry.
It's a new thing.
This. I'm explaining this, how to, now we found out to do the HT, okay, this dynamics. Now, how do you go back to W? Okay.
Yeah, that's cool.
So how do you go back to W? The idea is you can find an initial condition, H0, which will depend on W and on T, so that after some time T, the 3 first moments matches exactly. And the 4th moment almost matches, okay, up to an order which is small. And now you just do a linear numeric change. So what does that mean? You have your matrix full of HH, and one by one, you're going to move and transfer entries of W. And you can hope that an eigenvector won't change too much if you change one entry by something that kind of looks similar to it. Okay, that's kind of the hope. And that's what you do. But there is a big problem, is that eigenvectors, when you look at the derivative with respect to one entry, it's pretty bad. especially because the lambda k minus lambda L. If eigenvectors are very close together, then this is huge. It explodes, and you have a problem. So that's one reason why you need to control very finely the eigenvalues to understand eigenvectors, because of this derivative, basically. So maybe here I'll go quick, but how do you try to solve this? Well, you regularize the eigenvector. Instead of considering the eigenvector, you look at the resolvent, which are integrated over one interval. And the interval has to be small enough to contain only one eigenvalue. And this is correct. Okay? These type of equalities are true as long as the interval has only one eigenvalue. So now you need to control the fact that a small interval has only one eigenvalue. Okay, and this is not easy, but this can be done. Okay, so there's been many papers to prove this. And you can prove indeed that the probability of the number of eigenvalues which are very small, very close together, as only one is big enough. Okay? And this, for instance, gives you the convergence to a Gaussian. It is good enough for that. But however, you have one problem.
Just use this in this paper, right?
Yeah, basically, yeah. You do okay, UK, you change UK into this image file, and then you transfer that exactly. That's pretty much exactly. That's what Knowles and Yin did in 2011. However, if you want the square root log n, the optimal one, and you want n minus d as fast as you want here, and you cannot use that because this is a certain number, right? You cannot do any n minus d. You have a problem here. So how do we manage to circumvent that is to prove what we call, I guess, overcrowding estimates, which is maybe the probability of having, if I want n minus 3 here, let's say, I can maybe say that the probability of having 10 million eigenvalues in one small interval is n minus 3. Okay? But as long as it's a constant, you don't lose the constant here and you're good enough. That's kind of the idea. Of course, you have a very bad constant, but you have still only a constant. Okay? So that's what we proved in this paper based on previous paper included by Ben and Yao in 2015. And so that's the overall idea. So finally, for keeping the constant, you can also regularize in a different way. There was an idea by Ben, Patrick, and Jake in 2018, where you do a free energy regularization. You say the maximum entry, well, is basically close to this free energy thing if beta is large enough. And this way you can transfer the estimate because it's smooth now. It's smooth, so you can do this kind of Lindenberg exchange, control the derivatives, and you're good in. Okay. So that's all I wanted to do. So thank you for your attention.